Welcome to the SAR channel, where sound and audio are demystified. Even though the internet is reducing their influence, radio and television still remain important in our daily lives. In some areas, they are still the main source of information and entertainment. Traditionally, radio and TV signals are sent from land-based towers that broadcast on specific frequencies to local audiences. These services can also be delivered across the entire country through satellites. Beyond that, satellites play a major role in supporting worldwide telecommunications. In satellite communication, information is sent over thousands of miles, either to a single receiver or to millions, using satellites in space that act like automatic relay stations. Geostationary satellites follow a special orbit above the equator, moving from west to east at the same speed the Earth rotates, so they appear fixed in the sky. These systems use microwave frequencies to transmit signals. Audio can be sent as basic 7.5 kHz voice audio, 15 kHz audio, or other formats. A satellite's transponders take in the uplink signal from a ground station and send it back to Earth, where a downlink station receives it. Satellites use solar cells to get power from the sun. To stay correctly aimed at Earth, a geostationary satellite must rotate once every 24 hours. Small thrusters provide this spin when the satellite is first placed in orbit. For cube-shaped body-stabilized 3D satellites, 3 internal gyroscopes control their position along 3 axes and make adjustments when needed. Interestingly, twice a year, all geostationary satellite downlink stations experience short solar outages, about 5 minutes, when the sun, the satellite, and the Earth station line up exactly. During this time, the antenna's feed element casts a shadow at the center of the dish, and interference from the sun weakens the signal. In many cases, satellites send programs from one location to just a few others. Direct broadcast satellite (DBS) systems work differently. They send signals from one point to many homes. Each household uses a small dish antenna and tuner to receive broadcasts directly from a geostationary satellite. The satellite gets digital audio and video signals from ground stations and sends them straight to viewers. A DBS receiving setup includes an offset dish that gathers the satellite's microwave signals and a converter at the dish's focal point that changes those signals to a lower frequency. DBS systems use the Q band, which is a higher frequency range than the VHF and UHF bands used for regular over-the-air TV. Each DBS channel has a bandwidth of 27 MHz. Analog broadcasting comes from the early days of audio technology, but in 1986, the first test of digital audio broadcasting took place. After this test, the industry created digital audio radio, also called digital audio broadcasting. Instead of using analog methods like AM or FM, DR sends audio in digital form. It is meant to replace traditional AM and FM by offering a stronger, more reliable signal that resists issues such as multipath interference. Along with the audio, a DAR system can also send extra data, such as text, graphics, or still images, making it possible to deliver radio with pictures. Radio signals are sent either as analog or digital baseband signals that modulate a high-frequency carrier to carry information. A receiver tunes to that carrier and demodulates it to recover the original baseband signal using IF modulation methods. Digital broadcasts use a digital baseband signal, often compressed to reduce data size. The digital data changes a property of a carrier wave, its amplitude, frequency, or phase, and the modulated carrier is transmitted. Before modulation, several baseband signals can also be combined or multiplexed into one digital composite signal. In any digital audio broadcasting system, it's important to separate the roles of the source coder and the channel coder. The source coder compresses the wideband audio so it fits into a smaller amount of spectrum. The channel coder prepares this compressed data for radio frequency transmission so it can be sent reliably. A key job of the channel coder is adding diversity to reduce multipath interference, which causes flat or frequency-selective fading in the received signal. One method is frequency diversity, where the audio data is spread across several carrier frequencies so that a fade won't affect all carriers at once. Digital audio radio can be delivered in several ways. Like analog radio, it can be transmitted from towers, but digital systems are more efficient. Terrestrial transmission maintains the tradition of local stations providing local programming. These systems can be deployed quickly and at relatively low cost. Digital audio radio can also be sent directly from satellites. Programs are uplinked to satellites and then downlinked to listeners with digital receivers. These receivers use low-gain, non-directional antennas, making them easy to install in cars as small roof-mounted units. Nationwide satellite networks especially help rural areas and long-distance drivers, and they can also extend the reach of local stations. Some proposed satellite systems use multiple spot beams, each focused on a major city, along with a national beam. This allows both regional and nationwide programming. Building a commercial satellite system, however, requires large investment in satellites and ground equipment. In urban canyons or tunnels, extra local transmitters called gap fillers are needed to keep signals strong. Using single-frequency networking, these transmitters send the same content on the same frequency across adjoining coverage areas, and the receiver simply locks onto the stronger signal without interference. Digital audio programming can also be delivered through home cable systems. A major challenge for any digital audio radio (DAR) system is deciding where its broadcasts should fit in the electromagnetic spectrum. Usable frequencies are limited and mostly already assigned. The choice of DAR's frequency band affects its quality, cost, and how well it can work worldwide. Having a global frequency assignment would help manufacturers and reduce costs, but reaching worldwide agreement is not realistic. A universal satellite standard is also unlikely. Ideally, DAR would allow compatibility between terrestrial and satellite channels, whether the bands are close together or far apart. But in reality, no single band works perfectly for all needs, so any choice requires trade-offs. Another option is for new DAR systems to share spectrum with existing services. In this shared spectrum method, the digital signal is placed inside the existing FM and AM bands. Using an in-band approach, power multiplexing allows the digital and analog signals to coexist. Because DAR is more efficient, it can broadcast at lower power than the analog station. Analog radios treat the weaker digital signal as noise, while DAR receivers can pick up both digital and analog broadcasts. No matter how DAR is deployed, what happens to AM and FM broadcasting remains an issue. A transition period will be needed until analog radio slowly fades out. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Digital audio signals cannot be sent in standard PCM form because they would require far too much bandwidth. For example, a stereo digital audio broadcast could take up about 2 MHz, while an analog FM station needs only about 240 kHz. Because of this, digital audio radio, DAR, must use data reduction to greatly lower the bandwidth it needs. Many perceptual coding techniques can work for broadcasting. Although data reduction works well in many areas, the strict bandwidth limits of commercial radio make it especially difficult. Also, when an audio signal moves through a broadcast chain, it may be encoded and decoded several times, and each step can add distortion or create unwanted artifacts. The performance of a digital audio broadcasting system can be judged by several factors: the quality of the sound delivered, how far the signal reaches reliably, how much analog and digital signals interfere with each other on the same or nearby frequencies, signal problems in mountains or tunnels, deep fades at intersections, flutter from passing aircraft, data errors caused by man-made or natural noise, interference from power lines or signs, signal loss inside buildings, multipath distortion during both fixed and mobile listening, how complex the receiver is, and how much extra data the system can carry. Ideally, one receiver should work for both terrestrial and satellite broadcasts. Designers must balance many factors to create a system with low error rates, reasonable power use, and enough data rate while occupying as little bandwidth as possible. As with any digital system, keeping errors low is essential. Bit error rate, BER, is reduced through error correction data added to the audio stream and is checked at a given carrier-to-noise ratio. Digital signals can be received successfully at low carrier-to-noise levels, but analog signals cannot. Receiver performance is also measured by comparing the energy per bit received to the noise power in a 1 Hz bandwidth. Digital systems have brick wall coverage. The BER stays low and performance is good within a certain range, but a small drop in signal strength can suddenly cause very high BER and total failure. Most digital systems use pulse shaping before modulation to limit bandwidth. Pulse shaping applies low-pass filtering to reduce high-frequency content. This widens each bit in time and causes intersymbol interference, so raised cosine filters are used because they make this interference zero at the center of each bit interval. Multipath interference happens when the receiver picks up both a direct signal and one or more delayed reflections, for example, from buildings, which combine destructively. This causes frequency selective problems, and shorter wavelengths like FM are more affected. Multipath can also disturb the demodulated bit stream when delays are short. Frequency diversity helps fight multipath by spreading the data across multiple carriers so that interference on one carrier can be overcome by the others. 2 multiplexing methods are used. Time division multiplexing, TDM, lets multiple channels share one carrier by interleaving their data in time, even at different bit rates. Frequency division multiplexing, FDM, divides the spectrum into subbands, each modulated by its own carrier. A single channel can also be split across several carriers to reduce bitrate and errors, though this requires more spectrum. Phase shift keying, PSK, is commonly used because it gives the lowest BER for a given signal strength. A major benefit of digital systems is their efficient use of transmission power, which is seen by relating coverage area to the received carrier-to-noise ratio. The Eureka 147 digital audio broadcasting DAB system was chosen in 1995 as the European standard for broadcast to mobile, portable, and fixed receivers. This technology can be used for terrestrial broadcasts, hybrid satellite terrestrial systems, and cable delivery. Traditional radio uses one carrier frequency per station to send mono or stereo audio. While this keeps stations independent, it creates several problems. Large guard bands must be added between stations to avoid interference, and overall, this single carrier method is not very robust and wastes spectral space. Eureka 147 uses a different type of transmission coding that solves many of these issues. In Eureka 147, multiple audio channels are digitally combined, and their data is spread across many frequencies and times within a wide broadcast band. Instead of tuning to one carrier, the receiver performs partial fast Fourier transforms on the entire band and extracts the needed channel from many carriers. This design allows efficient use of spectrum and power and ensures reliable reception even when multipath fading occurs. In-band digital radio systems are hybrids because they let broadcasters send analog and digital signals at the same time. This allows analog radios to keep working while digital radios receive the new digital broadcasts. After a transition period, stations can shut off their analog transmitters and continue with all digital broadcasting. These systems have commercial benefits compared to wideband systems because broadcasters can keep their current listeners during the transition, reuse much of their equipment, use their existing frequency assignments, and avoid needing new spectral space. However, in-band systems are not compatible with wideband Eureka-style systems. They must match wideband performance, such as strong resistance to multipath interference, while facing the challenge of sending digital signals in the same band as analog broadcasts. In-band systems allow both analog and digital programs to be sent at once. Digital receivers easily ignore analog interference because digital signals are naturally resistant to noise. Analog receivers, however, have more trouble rejecting digital interference. Coexistence works if the digital signal is broadcast at much lower power. Because digital broadcasting is efficient, the low-power digital signal can still cover the same areas for digital receivers while remaining weak enough for analog radios to treat as noise. With an in-band on-channel IBOC system, digital signals are placed directly on the same FM or AM frequencies, while other systems place them on nearby channels. In-band systems fit within the same bandwidth limits as analog broadcasts and match the FCC's RF mask, where channel width increases as power drops. IBOC is appealing because it fits current regulations and business needs. Existing analog radios need no modification, and digital radios can receive both analog and digital signals. Since digital broadcasts can be added to existing equipment, setup costs are low. In-band systems offer better frequency response and lower noise and distortion within current coverage areas. If the digital signal drops out, receivers can automatically switch to the analog broadcast. Another method, in-band interstitial, IBI, sends low-power digital signals in the guard bands next to existing stations. This reduces the difficulty of separating the two types of signals. In a single-channel IBI system, the digital signal is placed in either the upper or lower adjacent channel. Both channels can also be used, though this reduces the number of available stations. Frequency hopping can then help fight multipath interference. In a single-channel multiplexed IBI system, several stations in one market combine their digital signals and broadcast them in neighboring channels, giving more frequency diversity and better protection from multipath interference. Separating the analog and digital signals is technically difficult, especially for IBOC. The digital signal must not disturb analog reception, and digital receivers must use special techniques to extract the weaker digital signal while ignoring the much stronger analog one. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. HD radio is a digital broadcast system called IBOC that the FCC has approved. Commercial radio stations use it to send digital signals over the same FM and AM frequencies they already use. Today, many stations broadcast both analog and digital signals at the same time on one frequency, a setup called hybrid mode. HD radio sends both audio and data from regular ground-based transmitters in the current VHF band, and these signals can be picked up by mobile, portable, and home IBOC receivers. For compression, HD radio uses a private codec called High Definition Coding, HDC. HDC is built on the MPEG-4 high-efficiency AAC codec, but the two are not compatible. HDC uses spectral band replication SBR to boost high-frequency detail while keeping coding accurate at lower frequencies. In FM-IBOC, the digital subcarriers are organized into different frequency groups. The FM-IBOC signal can be set up in several ways by adjusting how strong, fast, or data-heavy the audio and data streams are. In hybrid mode, low-level primary main PM digital carriers are placed in both the lower and upper sidebands of the FM signal. An extended hybrid mode adds more subcarriers along the inner edges of these main sidebands. In the all-digital mode, the analog FM signal is turned off, the primary main area is expanded with higher power, and lower-power secondary sidebands are added in the center of the emissions mask. To maintain time diversity, the audio program is broadcast on both the analog and digital parts of the hybrid signal. During encoding, after perceptual coding lowers the audio bitrate, the data is scrambled and sent through a forward error correction (FEC) process. FM stations can use three different methods to transmit FM IBOC. In high-level combining or separate amplification, the outputs of the analog and digital transmitters are combined and sent to the same antenna, though some power is lost because of signal differences. In low-level combining or common amplification, the FM exciter and IBOC exciter signals are merged and fed into a single broadband linear amplifier, which lowers overall power use and space needs. A separate antenna can also be used for the IBOC signal. An FM-IBOC receiver picks up both analog and digital broadcasts. Like an analog radio, it routes the signal through an RF front end and converts it to an intermediate frequency. Then the signal is digitized and shifted down to baseband. The analog and digital parts are split. A first adjacent cancellation, FAC circuit, reduces analog FM interference in the digital sidebands. The digital signal is then OFDM demodulated, error-corrected, decompressed, and blended before output. The AM-IBOC system aims to do the same thing as FM-IBOC, carry digital signals while staying inside the FCC emissions limits. But AM has far less bandwidth and is more easily affected by noise, so AM-IBOC faces tougher challenges. Like FM-IBOC, it supports both hybrid and all-digital modes to help stations slowly switch to full digital broadcasting. In the hybrid mode, pairs of primary and secondary digital subcarriers are added to the lower and upper sidebands, and tertiary subcarriers are placed inside the main AM mask. The digital carriers are kept 90 degrees out of phase with the AM carrier to reduce interference in a standard AM radio's envelope detector. The analog signal must be mono because AM stereo cannot work alongside AM-IBOC. In all digital mode, higher power primary carriers are placed in the center of the emissions mask. As with FM-IBOC, the AM-IBOC system can carry main audio, personal data services, station ID data, and extra application services. The hybrid system also uses time diversity by delaying the analog signal relative to the digital one. If the digital signal becomes corrupted, the receiver can briefly switch to the analog signal. Because of this delay, the analog broadcast may be unaffected by the interference that disrupted the digital part. The encoding process is the same as FM-IBOC. The audio is compressed, scrambled, error-corrected, interleaved, arranged into matrices, mapped onto OFDM subcarriers, turned into a baseband waveform, and then transmitted. The error correction and interleaving are tuned for the noisy AM environment. To carry digital signals properly, AM transmitters need enough bandwidth and very low phase distortion. They must also preserve the correct phase relationship between the analog and digital carriers. Since the center carrier is used as a reference, the system requires low group delay. Tube transmitters are not linear enough for AM-IBOC, but modern solid-state transmitters using multi-phase pulse duration modulation or digital modulation need only small input changes. Using one transmitter for both analog and digital is preferred. To reach radio listeners across the entire country in a cost-effective way, two companies, Sirius Satellite Radio and XM Satellite Radio, created systems that broadcast digital audio channels via satellites. This service is also called Satellite Digital Audio Radio Service, SDARS. Sirius Satellite Radio and XM Satellite Radio both started broadcasting in 2001 as competitors. After getting FCC approval, they merged in 2008, and today both services operate under Sirius XM Radio. XM Radio compresses music signals using a modified high-efficiency AAC codec, HEAAC or AAC+. The system's total data throughput is 4.096 megabits per second, with about 25% of the bandwidth used for error correction and concealment. Music channels are sampled at 44.1 kHz, while voice channels use 32 kHz. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.